Next, chapter 7, frequency domain analysis, control system engineering. Name of the chapter is frequency domain analysis of part 3, demonstrated by Arun Ranjan Naik, HOD Electrical, Neelachal Polytechnics. Okay, welcome to everybody. The magnitude plot is a horizontal line which is independent of frequency. The 0 decibel line itself is the magnitude plot when the value of k is 1. For the positive values of k, the horizontal line will shift 20 log k dB above the 0 decibel line. For the negative values of k, the horizontal line will shift 20 log k dB below the 0 dB line. The 0 degree line itself is the phase plot for all positive values of k. Consider the open loop transfer functions GSHS is equal to S. Magnitude M is equal to 20 log omega dB. Phase angle phi is equal to 90 degree. At omega is equal to 0.1 radian per second, the magnitude is 20 dB. At omega is equal to 1 radian per second, the magnitude is 0 dB. At omega is equal to 10 radian per second, the magnitude is 20 dB. The following figure shows the corresponding Bode plot. This one is the Bode plot. This is the diagram drawn between magnitude in decibel with respect to angle log omega. This is 0, this plan 0.1, 1, 10, etc. This is 20, this one is minus 20. This one is the line. Then phase angle phi is in degree with versus log omega. This is 0 reference line. This is 90 degree and this is horizontal to the log omega axis. The magnitude plot is a line which is having a slope of 20 dB per second. This line started at omega is equal to 0.1 radian per second, having magnitude of minus 20 decibel, and it continues on the same slope. It is touching 0 decibel line at omega is equal to 1 radian per second. In this case, the phase plot is 90 degree line. Consider the open loop transfer function. M is equal to 20 log square root of 1 plus omega square tau square decibel. Phi is equal to tan inverse of omega tau degree. The phase angle for the magnitude is 0 decibel and phase angle is 0 degree. For magnitude is 20 log omega tau decibel and phase angle is 90 degree. The following figure shows the corresponding Bode. This one is 20 magnitude decibel line and this is log omega line. This is 0, this point is 1 by tau, this one is 10 by tau, this is 20 decibel per decade. And similarly the phase angle phi is in degree with respect to log omega. This is 1 by tau line, this is 10 by tau point, this is 90 degree line, and the curve is like this. The magnitude plot is having magnitude of 0 decibel up to omega is equal to 1 and tau omega is equal to 1 t tau radian per second. From omega is equal to 1 tau radian per second, it is having a slope of 20 decibel per second. In this case, the phase plot is having phase angle of 0 degree up to omega is equal to 1 tau radian per second, and from here it is having phase angle of 90 degree. This Bode plot is called asymptotic Bode plot. As the magnitude and phase plots are represented in straight lines, the exact Bode plot resembles the asymptotic Bode plot. The only difference is that exact Bode plots will have simple curves instead of straight lines. Similarly, you can draw the Bode plots for other terms of open loop transfer function which are given in the table. Next, rules for construction of Bode plots. Follow these rules while constructing a Bode plot. Rule number 1, represent the open loop transfer function in the standard time constant form. Rule number 2, substitute S is equal to j omega in the above equations. Find the corner frequencies and arrange them in ascending order. Consider the starting frequency of the Bode plot as 1/10th of the minimum corner frequency or 0.1 radian per second, whichever is smaller value, and draw the Bode plot up to 10 times maximum corner frequency. Draw the magnitude plots for each term and combine these plots properly. Draw the phase plots for each them and combine these plots properly. Note, the corner frequencies is the frequency at which there is a change in slope of the magnitude plot. Example, consider the open loop transfer functions of a closed loop control system. Gs into Hs is equal to 10s by s plus 2 whole into s plus 5. Let us convert this open loop transfer function into standard term constant form. Gs into Hs is equal to 10s by 2 whole into s plus 2 plus 1 s by 2 plus 1 into 5 whole into s by 5 plus 1. That implies Gs into Hs is equal to s by 1 plus s by 2 whole into 1 by s by 5. Then so we can draw the Bode plot in the semi-log sheet using rules mentioned earlier. Stability analysis using Bode plot. From the Bode plots we can say whether the control system is stable, marginally stable or unstable based on the values of these parameters. Gain crossover frequency and phase crossover frequency, then gain margin and phase margin. First come to the phase crossover frequency, the frequency at which the Nyquist plots intersect the negative real axis is known as phase crossover frequency. It is denoted by WPC, that is phase crossover frequency is omega. Next, gain crossover frequency, the frequency at which the Nyquist plot is having the magnitude of 1 is known as gain crossover frequency. It is denoted by omega Gc. The stability of the control system based on the relation between phase crossover frequency and gain crossover frequency is listed below. If the phase crossover frequency omega Pc is greater than the gain crossover frequency omega Gc, then the control system is stable. If phase crossover frequency omega Pc is equal to gain crossover frequency omega Gc, then control system is marginally stable. If phase crossover frequency omega Pc is less than gain crossover frequency omega Gc, then the control system is unstable. Next come to the gain margin. The gain margin Gm is equal to the reciprocal of the magnitude of Nyquist plot at the phase crossover frequency. The gain margin is equal to 1 by phase margin, that is omega Pc, where omega Mpc is the magnitude in normal scale of the phase crossover frequency. Next, phase margin. The phase margin Pm is equal to the sum of 180 degree and phase angle at the gain crossover frequency. Phase margin is equal to 180 degree plus phi Gc, where phi Gc is the phase angle at the crossover frequency, gain crossover frequency. The stability of the control system based on the relation between the gain margin and phase margin is listed below. If the gain margin Gm is greater than 1 and phase margin Pm is positive, then control system is stable. If gain margin Gm is equal to 1 and phase margin Pm is 0 degree, then control system is marginally stable. If gain margin Gm is less than 1 or the phase margin Pm is negative, then the control system is unstable.